So, good afternoon, everyone. Welcome to my presentation on NULIMAS toolbox for seabed liquefaction. I would like to thank the organizers first, and it's really pleasure to be here. And my name is Ranjith Shanmugasundaram, and I'm working at Wiki GmbH, and I'm also a PhD student at TU Braunschweig. In this presentation, I would like to give a training session on the NULIMAS toolbox, which I have been developing for the project NULIMAS. And here is the agenda for the project. And the introduction, initially I will be giving you what is the liquefaction. And after that, I'll be describing about the numerical model that I have been developing so far, and which includes the bioequations. And these are basically the numerical model that the equations that I'm using. And after that, I'll be showing you the case where we could see the onset of residual liquefaction. And finally, I will be showing some of the cases where after what happens after the liquefaction. That's really quite new, and you'll be seeing later in the presentation. And to do along with the training session, the OpenFOAM Workshop, what I'm using is FOAM Extend 4.1, and you would also need ParaView in order to view some of the results. And then I'm using some of the post-processing steps using MATLAB or Octave code. And in order to get the code, you can also check it from this GitHub link, or also you can get it from this QR code. You just have to log into, you just have to check from the website under downloads, and you have the workshop repository, and you will find the entire code what I'm going to show during this training session. So what we will be learning today is initially to post-process in OpenFOAM, we'll be creating meshes for the seabed liquefaction. And then after that, I'll be showing you how we will be implementing the bioequations inside the OpenFOAM. And after that, I'll be showing you some of the cases to case setup just to see the test case study for the liquefaction. And I'll be showing you how to run the case using this numerical toolbox. And finally, I'll be showing some of the ParaView steps, showing the results in the ParaView, and then some of the function options like probes and sampling. So what does mean by liquefaction? Liquefaction is the process in which the soil behaves like a highly viscous fluid, and this happens mainly in case of unsaturated soil, where the soil is completely lack of air, and then it is completely filled with fluid. So what happens is that whenever there is a waves on the top, some loading waves, and the seabed is pushed up, and then the pore pressure there is between the soil grains, it is completely occupied by water, and then when there is a load on the wave, for example, for the waves, and this is pushed up, and then the pressure between the soil grains, which is the pore water pressure, it starts to increase, and then it goes on increasing such that when there is during the process, when there is heavy load, and then these water molecules between the soil grains do not have time to go out of it cannot squeeze out of the soil grains, and then it remains between the soil grains, and because of the high load, there is a high pressure is created, and then at some point, when it is the pressure is greater than the initial stress between the soil grains, this is when it is going greater than that, then this the bonding breaks. And because this bonding is helpful in order to withstand the heavy loads, for example, the structure as shown here. And once the soil gets liquefied, the pore water pressure increases, and then the shear stress increases, and then it breaks after some time. That is the case when the soil starts to behave like a highly viscous fluid. At that case, what happens is that the soil becomes very soft, and then it behaves like a fluid, and it cannot withstand the heavy loads, for example, structure. So this the structure starts to shrink down. For example, you can see in this picture that the soil after the liquefaction is starting to sink. Also, the process of the damages, for example, if there is a tight line, it starts to flow, something like that. So we need to avoid that. These are some of the examples of liquefaction. So, for example, you can see during this Christchurch earthquake, but these are the examples after the liquefaction during the earthquake in these liquefations. We'll be getting more about the seabed in these liquefations. Yeah, you can see some of the examples like the cars started sinking after earthquake, the buildings started to collapse after the earthquakes. These are some of the damages caused by electrification. So that brings to our project NULIMAS. In this project, what we do, like NULIMAS is actually the acronym for numerical modeling of liquefaction around marine structures, and you can also find the website here. And as a part of this project, what we do is we develop an open source numerical modeling software for liquefaction around marine structures. And we, of course, we'll be doing it in OpenFOAM, and then like we'll be calibrating, validating and calibrating this numerical toolbox. And during our project, what we will be doing is we will be also having a small scale test and large scale tests, like in order to calibrate our numerical model, what we are developing. So this is the main case study that we would be doing as a part of the project. And yeah, here is actually the gravity anchor. It is based on the seabed and which is connected to the turbine and then with the help of rope forces. So whenever there is a loading, you can see that the liquefaction starts to develop, and then like it is collapsing the anchor, and then we have like a lot of damages, and that we wanted to predict with our numerical model. So liquefaction can be classified into two types. The first one is residual liquefaction. So as I told you, it occurs mostly in case of progressive waves. Then during there is a periodic pressure variation to the seabed that is causing for the liquefaction. And there would be a shear stress and shear deformations that takes to the rearrangement of soil grains. And the pressure due to this rearrangement of soil grains and the pressure in the water starts to increase. And this, whenever the pressure is greater than the initial effective stress of the soil, and it starts to liquefy. So this is the residual liquefaction. And the next one is the momentary liquefaction, in which it mainly occurs during the passage of wave trough. And in that, what happens is that the unsaturated soil grains, the gradient, the pressure gradients are very large. And then the larger pressure gradients allows to generate the lift in the top layer of the soil trough. And this, if this pressure is greater than the submerged weight of the soil, and then the momentary liquefaction occurs. So this momentary liquefaction is actually a temporary event, and then like it will be just for a short period of time. And so like we are not concentrating much on momentary liquefaction in our project. So talking in detail about the residual liquefaction, this is the sequence of residual liquefaction process. What happens is that as I told you before, the pore water pressure increases. You can see that here the pressure starts to build up, and after some time the upward directed pressure gradient occurs, so that the pressure is greater at the impermeable base, and then like it is lesser at the top. And so due to this upward directed pressure gradient, what happens is that between the soil grains, the water tries to flow from the top, and then the remaining the soil particles tries to settle down at the bottom. So at some point of time, when all the soil particles settle down at the bottom, and that is known as the soil compaction. And so during this process, what happens is that once the pressure builds up, and like it starts to dissipate. So at the end of the compaction process, we can see that the pressure completely dissipates. And during using our numerical model, what we wanted to do is like we wanted to have a graph the pore pressure buildup and then the dissipation we wanted to capture with our numerical model. So the numerical model, what we used is the bioequations. So this case study is actually the one what I was showing you before. So we have the seabed, and then we have the structure on the top. And we would be numerically how we approach is that like we divide this into two different regions, the omega-1 and omega-2. In omega-1 region, we have the waves. So in the waves, how we are going to define is that like using the wave equations. And inside the soil region, we construct the soil as a poroelastic solid. And that one, like we would be using it we would be treating with the bioequations, which I'm going to show later. So once the pore pressure starts to build up, we have another region which is known as the liquefied region. And in that region, what we wanted to do is we just wanted to use Newtonian fluid over there. So like for the different types of approach for the poroelastic solid, we have three different approaches. What we have is the fully dynamic approach, in which we have we consider the acceleration of soil skeleton, and then like we have the acceleration of pore water related to the soil skeleton. And the next one is the partially dynamic model, in which we have the acceleration of soil skeleton, but the acceleration of pore water related to the soil skeleton is absent. And finally, what we have is the quasi-static model, where we don't have the acceleration of soil skeleton and then the acceleration of pore water related to the soil skeleton. And we would be using this quasi-static model because like we wanted to have very less number of parameters. And so this quasi-static model would give you, it's a very simple model. And this is a bioequations, it's a quasi-static model in which like we have two different equations to solve. The first one is pore fluid continuity. And in that, like if you can see that like there is the continuity equation over here. On the left-hand side term, you have this the Laplacian of pressure that comes out of this divergence of the velocity. And then the right side terms, what you have is actually due to the rate of change of the pressure. And because like initially we have as a compressible fluid, and then like we wanted to linearize it to an incompressible fluid. And that's why like we have the two different terms. And the first term is the dou epsilon by dou t term. This is due to the rate of change of volumetric strain. This epsilon term is a volumetric strain. This is the divergence of displacement. And this is due to the second term is due to the compressibility effects. And one more equation what we have is the linear momentum balance. In that what we say is the divergence of stress is 0. And in the divergence of stress, like we also have this pore pressure to in that. And for the stress, what we have is the normal linear model. It's just it's based on the elastic modulus and then the Lami's constant. And this is the expression for the compressibility. So whenever we have the saturated fluid, we just have 1 by K. And then like when it goes to unsaturated, we have like 1 minus S term coming up over there. And some of the features about the bioequations is that in that the fluid flow transport, we have the velocity. It is described by the Darcy flow, which means that it is directly proportional to the pressure gradient. And you can see that the bioequations are strongly coupled. So we have the volumetric strain term present in the continuity equation, and then the pore pressure term present in the linear momentum equation. And this is a linearized model. And initially, how we wanted to approach is that like we wanted to solve the pore fluid continuity equation, and then the linear momentum equations. And then finally, we wanted to check for the convergence. And then after that, like we'll be calculating the stress for solution. So in the OpenFOAM, what we do is like we can just simply implement this continuity equation with this approach over here. So you can see that in the pore fluid continuity equation, we would be solving for the pressure. And so we have this implicit terms for the terms involving pressure. And then like we have this explicit term for the terms involving for the displacement. And the next one is the linear momentum equation. In that, what we have is the stresses. The divergence of stress is 0. And then we have this sigma dash prime is the effective stress. And like we need to separate the pore pressure because it would be contributing together with the normal stress. And these are the equations for the stresses what we use. It is proportional to the strain, and then like we can implement into the OpenFOAM using this code shown over here. So in that first case study, what I wanted to show is that we wanted to verify the bioequations, and then we wanted to validate that against the analytical model what we have, that is from Hugh and Ying's case. And in that, what we do is like we consider a seabed, and then like we switch on the waves on the top, and then so that's why like we have for the pressure we have a wave boundary condition, and then for the displacement we have the traction free condition, which means that it is free from the external stress. And at the sides of the seabed, like we have cyclic boundary conditions for the pressure and then the displacement. And at the impermeable base, what we have is the gradient of pressure is 0, and then the displacement is 0. So the gradient of the pressure term, what it does is like it doesn't change the pressure across the boundary. So, and in order to have the different boundary condition, what you see here is the progressive wave for the pressure wave. And in that, like we just simply implement with kind of the wave equation, and we just like implement inside the uh, boundary conditions, and we have different we can feed in with the different amplitudes and then the different magnitudes, like whatever. Also, we can do with the different phase shifts. And the next boundary condition, what we have different is for the displacement, in which we have the traction displacement. What we say is we give the traction the stresses. It says that like it is free from the external stress, and then like in that, like using the stress strain relationship, we can get the gradient term. So we can get a kind of a Neumann boundary condition over here, and that can be directly implemented in the OpenFOAM. So here, like I would wanted to show with the case study. You can check out the code. You can download the code from the link that I showed before, and you can see that you have the two different folders for the source code and then the tutorials. And in the source code, you can see that there are different solvers. In that, we would be solving with the bioequation solver, and then the residual liquefaction solver for today. And you can see that like inside the boundaries, you can see the different boundary conditions what we wanted to implement for these cases. And I have given all WMake script. You can just simply run that script in order to compile all the solvers. And also, first you need to source the foam. And yeah, you can just do all WMake in order to compile all the solvers. You can see that like all my solvers are already compiled. And the next step, like what you wanted to go is like you just have to go into the tutorials. And I have the first case. I just wanted to show you the first case right now. And in that, what I want to do is to validate the pressure and then the shear stresses. So I just clean the code for now. And here in the constant, first we wanted to do the block mesh. So what we do is like we need to create a block mesh for the seabed, and in that the length of the seabed will be equal to the wavelength what I wanted to do, and then the height of the seabed would be the domain's height, and this can be seen from the constant polymesh block mesh file. So in that you can see for the X, I have given 122.025 meters. That is the length of the seabed, and then the 50 meter is the height of the seabed that I wanted to simulate for now. And here you can see that I have just given a rectangular block with 100 by 50, 100 in the X direction, and then the 50 by 50 cells in the Z direction. So I have given different boundaries for the seabed. Seabed soil domain bottom is for the impermeable base, and then I have for the sites I have cyclic boundary conditions. After that, like I wanted to show you in the constant, we also have the wave properties file where we would be giving the list of the wave properties that we wanted to use in this model. That like what we have is the wave height of 6 meters, and then the water depth is 20 meter. And we have that direction is just to show that like in which direction the wave flows. And the period what we have for the wave is the 10 seconds. And as I shown you before, the wavelength, what I'm considering is like 122 meters. And what we have to do is we just have to run the all-run script. In that all-run script, like I have I have the block mesh and then the buyout QS form. And the first we have to run the block mesh, and then like finally we have to do with the buyout QS form. I'm just going to do with the all-run file. While it is running, we can just check the block mesh, how it looks like. So I'm using ParaView in order to look the block mesh file. So here you have the case, the block mesh, and you just have to do the surface with edges. You can see the mesh file, and you can see that you can just turn on this data access grid in order to just check the domain size. You can see that in the X direction, I have 122.025 meters of meter length of seabed, and then the height of the seabed here is the 50 meters. And I think it started to run, and can I just close the screen over here? The screen. Yeah, okay. I think that is fine. Yeah. So next, looking at the system control dict file, you can see that you have to give specify the start time and then the end time. I'm just running for 20 seconds, and then the time step size I'm using is 0.2 seconds. And I have the write control for adjustable runtime, so it will be writing all the parameters like after 1 second. So you can see here the pressure. So here the amplitude of the pressure is somewhere between minus 1900 uh, you can just simulate the video here, just in order to see the wave. And I'm just using a wrap by vector field in order to just show you the waves. So you could see the wave flowing over there. And yeah, let me close the para view. And here, like I had used some of the function objects in order to show the results of the pressure. And for that, like I have to specify this function objects in system functions file. So what the function objects that I have is like I have the sampling, and in that, like what I do is from uh, at the middle of the domain, 61 meters, I have set up the field. So it will be for the pressure, displacement, and then the shear stress. The toolbox that like what I use here is the shear stress. And so in the system control deck file, like I have this, I have included this functions file just in order to have that while running. And so since I have since I have used the function objects file, you can see the post processing. In that post processing, you can see it's writing out all the pressure file, and then the shear stress results in the post processing. So you can see that like it runs from 0 to -50. And the first code is actually the pressure, and then the second one is actually the shear stress. Now, what I wanted to do is like I wanted to compare that against the analytical results, and for that, like I have the octave code, so comparison over here. And for that, like what I do is I just go into Octave, and then I run the comparison file. So I have two different plots. The first plot, yeah, much better. The first plot is for the pressure. You can see that like the dotted lines are the analytical results, and then the red line is the results from this post-processing file. And you can see that the results are pretty matching good with the analytical results. This is for the pressure. And then similarly, if you see for the shear stress, you can see that the dotted lines are the analytical results, and then the dark red line is actually from the numerical results. You can see that the results are matching well with the analytical results. Okay, moving further. So you can see that the pore pressure and then the shear stress shows very good results against the analytical solutions. And coming next to the residual liquefaction, so still now like what we see is the pore pressure does not build up. Like in order for the pore pressure to build up, like we need rearrangement of soil grains, and these bioequations does not include the rearrangement of soil grains. And this shear stress and deformations would actually would rearrange the soil grains, and we have for that like we after that like we would get the accumulation of pore pressure. And for example, like if you see in this equation here, the PC is actually the pressure what we were seeing still now before, and then this capital P is the one for the accumulation of pore pressure. And you can just see from this graph, this PC, the bottom line is actually the curly wave is actually the pore pressure, and then the capital P is the pressure buildup. You can see that the bio equations can just capture the if you see from the results from the paraview, it was always between minus and positives, and there was this the pressure, and later we want the rearrangement of with the rearrangement of soil grains, like we will be having this pressure buildup. For that, like what we do is like we have the accumulation of pore pressure equation, and this one it contains it's just the Laplacian equation with this this coefficient is the coefficient of consolidation, and from this coefficient of consolidation terms is basically emerging from the properties that we provide during for the bio equations. And finally, this we have this additional source term. This source term is contributing for the pore pressure buildup. And this is the CV is the consolidation equation. And you can see that all those variables are coming from the bio equations, the material properties. And this F is actually the source term. This source term is actually the ratio of initial effective stress to the number of cycles for liquefaction times the time period. And this sigma 0 dash is the initial effective stress. So this is basically the stress what the soil has at rest. And for that, like we would be using we can calculate it from the equation over here, in which we have the gamma dash, which is the specific weight of the soil, and then K0 is actually the lateral effective stress. And finally, the other term what we have from the source term is the number of cycles for liquefaction terms, NL. And this term is actually based on the amplitude of the shear stress, and then on the alpha and beta. These two coefficients are from the relative density of the soil. And how we do for the amplitude of the shear stress is that, like initially we don't have the just for the complete wave cycle, we don't have the amplitude of shear stress. So for that, like we need to wait for one wave cycle, and then like once after that, we just calculate the root mean square of the shear stress, and then like from that, like we just work out to get in order to get the amplitude of the shear stress from the equation showing here. But how do we get the liquefaction? So for that, like we have this criteria that whenever the pore pressure buildup is greater than the initial effective stress of the soil, and the soil will be liquefied. So that's what like we have seen already, that whenever the soil is greater than the initial effective stress of the soil, and then the soil starts to move freely with respect to each other. So that's the concept of liquefaction. And here you can see this the pore pressure buildup term, and yeah, this is how it has been implemented in the OpenFOAM. And just we have the Laplacian equation. So we have the implicit terms from the PE, and the capital P here is in the code it is written by PE, and then we have the source term implemented over here. So the difference from the earlier equation is that still now what we do is we didn't have the pressure buildup equation, but here in order to have the residual liquefaction, we will be solving the pore fluid continuity equation. After that, the linear momentum as same as earlier. After that, we will be checking for the convergence, and finally we'll be calculating the shear stresses. And after that, we will be solving this additional equation that comes what I shown in the previous slides. And we will be calculating the pore pressure buildup equation, and then we will be applying the criteria in order to check whether the soil is liquefied or not. So we have the same seabed over here, and then what we have is the wave. We just have the same boundary conditions for the pore pressure and then the displacements all over the place, and then we have an additional term which is the capital P, which is the pressure buildup term. And we can see that the boundary condition what I use here is at the seabed for the pressure buildup is 0, And at the sides of the seabed, like have the pressure buildup is cyclic, and at the bottom we have this the gradient of pressure of pore pressure buildup is 0. So here are the list of properties that I have for the residual liquefaction model. And yeah, these are same, the seabed properties and the wave properties is from this paper. And in that, like I have these seabed and wave properties are similar to what I have been showing for the previous case. And but for this, we have the additional pressure buildup. For that, like I have few other properties, the relative density of the soil, and then the relative density of the soil, the coefficient of lateral stress, and then the submerged specific weight. And yeah, from the relative density of the soil, we could calculate the coefficients what we had in the number of cycles of liquefaction term. This is the alpha and beta coefficients. And yeah, next I just wanted to show you the case. Yeah, going to the next case, we can see case two liquefaction. And here, what we are going to do is we have the same Aldrin script, but we have instead of BioQS form, we have the residual liquefaction form, so which also includes the pressure buildup term, and also it calculates whether it is liquefied or not. So regarding the material properties, you have the I just forgot to show you during the last case study. You can see that here you have all the list of material properties inside the constant folder. And here you can see the list of material properties that I have been using for the model: the elastic modulus, Poisson ratio, permeability, bulk modulus, degree of saturation, and yeah, some other properties as for the previous case. But here in this case, like we'll be having the additional properties like the coefficient of lateral stress, the submerged specific weight of the soil, and then the relative density of the soil. And the wave properties for the soil is same as earlier. So we would be using a 12 centimeter wave height and the water depth is 55 centimeter. And I think I will be just increasing the wave height just in order to have the liquefaction. Just have to run the all run script. You can see the case is running. And here you have similar to the previous case, like I have created a function object in order to post-process some of the pressure buildup values. So I have that here in system functions file. In that, like I have probes at the middle of the domain at like different seabed depths, starting from 8.5 centimeter to 40 centimeter. Let us look it into the para view file. You can see the similar seabed, and here in the fields, you can see the different liquefaction criteria, and then the number of cycles for liquefaction, the additional terms other than in the bio equations. And if you just look into the liquefaction criteria, I'm just rescaling it between 0 and 1 just to check for the liquefaction. Now you can see that the pore pressure is increased. The pore pressure has increased. The pore pressure you can see from the PE field. So you can see that as the time progresses, the pore pressure starts to increase. The pressure starts to build up, and the liquefaction criteria from that, like you can see that also starts to increase. And so you can see that whenever it is red, the liquefaction criteria is crossed above 1, and then the soil gets liquefied after that. And you can see that the liquefaction starting from the top of the soil, and then like it progresses slowly towards the bottom of the soil. So moving further, we have this if you see the liquefaction process, like what we have seen till now only is till this part. So the pore pressure starts to increase, and then it starts to behave like a fluid. So in the next steps, like what we will be seeing is like how we wanted to treat this soil after it gets liquefied. In that, like we will be using the driftflex model. So in that, what we do is like it treats as a single fluid. So instead of having two different phases, like it just considered as a single fluid, the pseudo single fluid, and like you have the two. But like if you have to do for the two phases, like you will have two momentum equation, two continuity equation, and then like there is a momentum transfer and everything. But this reflex model, it solves as a one single fluid, and yeah, you have one continuity equation and then one momentum equation. And like you will be having additional equation for that, like, and you will be seeing in the next slides. And like you have this kind of model is mostly used in case of sedimentation, fluidized bed, or other flows in which the relative motion is primarily controlled by the buoyancy forces. And the Difflex model is it's pretty much simpler than the two fluid formulation. So in the equations, like what we have is the density is the mixture density. Everything is a mixture fluid, and how the subscripts like what I have here, like with the M is the mixture, and then the C is the continuous phase, and then the D is the discrete phase. The C, what I have used is actually the water, and then the discrete phase D is actually the soil. And you can see that the total amount, the alpha is actually the amount of particles, and alpha C is the volume of soil, volume of water, and then the alpha D is the volume of soil grains. And you can see that the total sum is 1. And with that, you can derive the how much amount of pressure it's contributing for the mixture, from the continuous phase and then the discrete phases. And similarly, you have the equation from the for the velocity. And you can just, if you compare with the equation model, you have the continuity same like that, and then the momentum equation. Here, the continuity equation is similar like the normal Newtonian fluid, but in the momentum equation, you can see that in addition to the normal equation, like you have an additional term. This is from the drift flux. And additionally, you have this drift flux equation. This is how it determines how the amount of soil particles or it changes. And if you just compare with the bioequation model, if you have the continuity equation, comparing, if you can just compare that similar to the bioequation, and like you have the additional terms. And then we have the similar momentum equation in the bioequations. And then like in the drift flux model, what we wanted to use is, we wanted to change, say such that the soil particles it remains constant and the porosity doesn't change. And this is how we implement inside the OpenFOAM. And we have the continuity equations, momentum equations, and then the flux continuity equation. And whatever you see here in the red color term is switched. It's from the liquefied region, and then the blue color term is actually in the solid region, and finally the black color terms will be solved both in liquefied and then the non-liquefied regions. And yeah, so in the OpenFOAM, how we implement is we just use the indicator function. So we just turn on and off the terms when it liquefies and when it doesn't liquefy. So the similarly, the boundary condition, like what I use for this model is we have the additional terms for the velocity, and this is same related to the previous model. But once we get once it gets liquefied, like we wanted to divide the regions, so the liquefied and then the non-liquefied regions. So whenever between the liquefied and the non-liquefied regions, like we using the dynamic mesh, we need to create a boundary between them. So you can see that we have between the regions, on the top is the liquefied region, and then the bottom is the solid region, and then like we have boundary conditions between those regions. So how we do the dynamic measures that we calculate the accumulation of pore pressure, and then we can see we see that we check for the liquefaction criteria, and then once it gets liquefied, so you can see that whenever it gets liquefied, there will be a phase cut identifier, like it goes toward all the phases, and then it checks for the region which is liquefied or not, if it is liquefied or not. So in the neighboring cell and from the owner and then the neighboring cell, it checks like whether it is liquefied or not. So like if it is different between the neighboring and then the owner cells, like it just creates a boundary between the regions. So it automatically changes. Just you can see that like on the right hand side, I have the animation for that, and you can see initially it is completely solid, and then like after some time you can see that it gets liquefied, and then you can see the red color region coming up. Yeah. And once it gets liquefied, like it automatically creates a boundary between the liquefied and then the non-liquefied regions. This is the case study that I have for the compaction model. So what we do is we just have the same set of parameters for seabed and wave properties, and then we still use the same pressure buildup properties. But further for the post liquefaction, like we have the settling velocity, and that term is actually deriving from the for the drift flux model, and this is actually the closure that we use for the drift flux. So what we say is that it is dependent on the amount of soil grains, and we use this 1 minus alpha power q. This is the term uh, for the closure for the drift flux, and it is depending on the settling velocity. And now I would like to show the case study that that I would like to show for the compaction. Here you can see that inside the constant folder, like you have the same wave properties, material properties, and then but like we have this additional dictionary for the dynamic mesh. So if you run the all run script, you can see that it is running. Yes. You can say whether the expression occurs. So you can see that here it starts to liquefy. So, and what I wanted to show you is that like it automatically creates a boundary between the liquefied and non-liquefied regions. This is I'm just showing the boundary between the liquefied and then non-liquefied regions. So you can see that like it is automatically creating the boundary uh, between the liquefied and then the non-liquefied region. And here, like what I have this alpha is the amount of soil particles in the seabed. You can see that once the soil gets liquefied, the amount of alpha it starts to increase at the bottom. So it's because the amount of soil grains it's starting to settle down at the bottom, and then the water starts to come up. So that's what like I was showing you earlier. And then the how we get to the compaction is that like whenever the soil grains, the amount of soil grains reaches this much some amount, and we say that the soil is said to be compacted. And then once the soil gets compacted, we say that like it again turns back to the solid state. Then like we'll be solving the bio equations again inside the soil region. This is the pressure plot like that you would get at the end of the simulation. And like if you just run the Octave script, like you will be getting this. And you can see that the pore pressure starts to increase. This is during the liquefaction stage, and this is similar to the sequence the slide that I was showing you before. During the sequence of liquefaction, the pore pressure is starting to increase, and then like after that, and then it starts to the pore pressure will be dissipating. And these are the charts at like different depths of the soil. And then you can see at the bottom of the soil, it takes a long time to liquefy. And then like the soil compaction starts from the bottom of the soil, and then the pressure dissipation starts. So once it gets compacted and the pore pressure starts to dissipate, and this is the region when it gets compacted. You can see that the soil, the pore pressure is starting to dissipate. And so I would say that like we would able to capture the soil seabed, the liquefaction and then the compaction with our numerical model. Yeah, that brings after that, like I have this one for the liquefaction depth. You can also with the code you can also check for the how much amount of liquefaction we have at the moment. So this is the chart like I was running is for 30 seconds. And you can see that initially the seabed depth, it's a liquefaction depth. And once initially after 5 seconds, it starts to completely liquefy. And then like after that, like you can see that the compaction starts, and then the soil at the bottom of the soil is soil again. And then it increases and it reaches to the point somewhere around 4 centimeters. So it's that the soil is completely compacted, and we have just less volume of soil, and so the pore pressure completely gets dissipated. Yeah, that brings me to the end of the presentation. Before, I would like to conclude that this numerical toolbox, we were validating the analytical solutions for pore pressure and then the shear stress. And you can see this, the toolbox shows the very good results in predicting the onset of liquefaction. And also you can see that after the liquefaction, we were using the dynamic mesh in order to have the two different regions for liquefied and then the non-liquefied regions. And after that, we were using the driftflex model inside the liquefied region. And finally, this NULIMAS toolbox can capture the liquefaction, which is turning from the soil to liquid, and then finally to the compaction from liquid to soil. Thank you.